Hello, everybody, and welcome to the second session of SVR 2020. This year, for the first time, we are doing this remotely, and I hope all of you are safe. And let's start doing this. In this session, we have five full papers, all of them in the VR evaluation and testing. And the protocol here is that we will present a 7 minutes video of each one of the works, and then you have 3 minutes for questions. Questions can be posted using Wova, or also, if you prefer, in the YouTube comments section. And then let's start it. And the first paper is the eye tracking data analysis for visual exploration, assessment, and decision-making interpretation in virtual reality environments. And the presenter is Abner Cardoso da Silva. And let's start this.
Greetings everyone, my name is Abner Cardoso da Silva. I'm a master's candidate at Pontifical Catholic University of Rio de Janeiro, and today I present the work entitled Eye Tracking Data Analysis for Visual Exploration Assessment and Decision-Making Interpretation in Virtual Reality Environments. Well, first of all, what's decision-making? Decision-making is a cognitive process necessary to make choices. It's composed of multiple steps, while some of those steps may require the processing of visual information, such steps as gathering information or choosing among alternatives. In this context, eye tracking is a technology that has been used by psychology as early as the second half of the 1900s to better understand the human cognitive process. Eye tracking is a type of sensor that identifies the direction and position of eye gaze on some kind of stimulus, where a stimulus can be any type of visual information, such as image or a video on a screen. Recently, the VR industry has integrated eye tracking into VR devices as a way to further improve the user experience. However, the combination of VR and eye tracking have been shown to be a powerful tool for research on human cognition, as VR enables the creation of controlled environments and eye tracking gives new insights on user behavior on those same environments. Some researchers state that eye tracking research applied to virtual and mixed reality only focus on a small portion of eye tracking metrics. However, there is a large number of eye-related metrics that may provide meaningful information about one's cognitive states. Therefore, our objective is to investigate eye tracking data, metrics, and methods to support decision-making interpretation in VR environments. So, we developed a Unity application and tested it with volunteers from Techgraph Institute at PUC Rio. In total, there were 10 volunteers and each were subjected to 2 different scenes. The first one had no kind of distraction, and the second presented audio and visual distractions. In both scenes, each participant had to solve a set of Raven's progressive matrices. In this kind of test, the subject is presented with a figure containing a blank spot, and the objective is to identify from a set of options which one fills the blank spot. Each set contains 50 RPMs, and for each RPM, 10 features were calculated. Finally, after each scene, every participant were asked to fill a simulation sickness questionnaire. From the raw data extracted in the Raven's progressive matrices, we classified some basic elements, and those were fixations, that are points in the stimulus where the eye rested for about 300 milliseconds. It defines points where information is being processed. In the figure on the right, fixations are represented as colored circles, while the color and size represents the time spent on the fixation. Saccades are transitions between two fixations. They represent the search for information. In this image, they are represented as arrows connecting two circles. Scan paths are the full structure composed of both the fixations and the saccades. It's useful to visualize the trajectory over the stimulus. And areas of interest that represents points with some kind of attention-gathering property. They may or may not be defined by the researcher. In our case, we defined the area of interest as the option with the right answer. This image shows how the RPM were presented in the application. The answer is chosen by pointing and click with a remote controller on one of the buttons on the right side of the screen. This is the first scene where we tried to reproduce an office and didn't include any type of distraction. And this is the second scene, with objects and an avatar that interacted with the environment and produced sounds. Those were the metrics used in this study. Besides the two most common fixation and saccade count, we evaluated other 8 metrics related to scan paths and areas of interest. The time to first fixation on an area of interest and the on-target fixation, that is, the number of fixations in an area of interest, showed an inversely proportional relationship. As the questions became harder, the time necessary to identify the right option increased, meanwhile the number of fixations on the right options decreased. So in harder questions, the decision was taken without enough inspection of the answer. For questions answered correctly, every participant spent more time fixating on the right answer, showing that a more in-depth evaluation was done before deciding. The spatial density, a metric that shows how much of an image was observed, had a significant increase in the second scene. This could mean that for most participants in the second scene, the exploration was more sparse. This was an exception for participants 2, 5, and 10 that presented a decreased value in the second scene. But those 3 reported in the simulation sickness questionnaire that they felt sick in the second scene. So this may have affected the exploration process. The first limitation was the coronavirus pandemic. It had some negative influences over the number of volunteers. As the experimentation was conducted in the early stages of the quarantine, not many people were willing to participate. The second limitation was some flaws in the implementation of distractions. Not every participant noted the visual distractions. Thus, we presented some interesting behaviors in other features besides the absolute number of fixation and saccades, and would like to state that there are many other features besides the one presented in this work that may provide deeper insight in decision-making analysis. As future works, we plan to recreate the visual distractions to explore new features and new tasks, and evaluate the eye-tracking features and visualizations in 3D environments.
Abner. We are waiting for questions here in the comments, or you can also ask Abner in the WOVA application. I have a question for you. It's a very nice work. We have this kind of eye tracking for HMD devices from just some time, and it's not so easy to see works exploring this kind of device and this kind of analysis in VR. And
Yes.
the target, your targets were always in a plan, isn't it? In the
Yes.
first scenario, please. In the second is the
No,
same.
in the both scenes, the target was a plane. The main focus was to solve the RPM in this plane presented in front of the player.
And why are you using the targets in a plan and not, I don't know, in this space?
Well, actually, we developed a 3D visualization using 3D points on mesh of objects in the scene, but we had some problems with the data collected, and we couldn't include it in the study. But we plan to develop 3D visualizations and data analysis in further studies.
Okay, thank you. And what kind of a recommendation for the use of eye tracking in VR can you say for the listeners?
Well, I think that the most important is there's an author that his name is Kenneth Honkovich. I hope I'm pronouncing it correctly. That he published a book entitled "Eye Tracking: A Comprehensive Guide to Methods and Measures," that covers most of the difficulties new researchers have with the field. So I think that anyone that is
Yeah.
starting is, yes, in eye tracking, not in VR, but eye tracking in general.
Mhm.
So for anyone that is trying to apply eye tracking to collect data in VR or in traditional 2D displays, I think that's a good start.
Yeah. Okay. Yeah, I'm curious about the how well it works and the idea of change the depth and not only the disposable
Yeah,
in the planes.
it's still in early stage, so it has some flaws, but it's very precise and accurate.
Okay, thank you very much, Abner, and
Thank you,
congratulations for your work.
thank you.
Let's go to the second paper. And the second paper will be presented by, just a minute, I'm trying to find the name. Okay. The second paper is the virtual look around, suitability evaluation for virtual tour in multiple platforms. And it will be presented by Jean Cheiran. Let's go.
Hi everyone, I'm Jean Cheiran, professor at the Federal University of Pampa, and I'm going to present the paper Virtual Look Around, Interaction Quality Evaluation for Virtual Tours in Multiple Platforms. Adriel Rodrigues, the first author, graduated from Unipampa with a bachelor's degree in software engineering. Technologies for virtual reality have evolved over the last 50 years, allowing more users to experience VR applications for leisure. Particularly, virtual tours have become popular, as they allow users to look around places far away in space and time. Nowadays, for instance, searches for the term virtual tours on search engines increased 7 times, mainly because of the COVID-19 outbreak. Such VR environments can be visited through non-immersive devices like desktop computers, or immersive ones like VR headsets. Each device will provide the visitor with a different experience by creating a different level of the sense of being there. But to what extent is this experience different? This can be a relevant question for an educational institution that wants to use virtual tours along the school year, or even for a regular user who wants to decide based on a cost-benefit analysis. So, in our research, we aim to answer these questions. Is there any difference in the interaction quality reported by users of virtual tours among different devices? And is there any difference in users' performances among different devices? Now we will explain how exactly we carried out our experiment. First, we created a virtual tour of the Unipampa's facilities in Alegrete. We took nice 360-degree pictures of our campus using a Samsung Gear 360 camera. We chose WebXR API and the React 360 framework in order to easily run the virtual tour on different devices. The entire tour contains 90 scenes. So, we developed 4 different tasks in the VR tour with different difficulty levels and different lengths. The more complex a task, the lengthier it is. Also, harder tasks demand to explore some scenes fully. Here, we can see the first task, the easy one, that involves counting the number of dogs at the Unipampa's secondary entrance. The teleportation technique was applied to navigate between scenes. Next, we chose the platforms to compare the user's experiences. The non-immersive devices are the 5.5-inch screen Asus ZenFone with touchscreen navigation and a 14-inch screen Asus laptop with mouse navigation. The immersive devices are the Google Cardboard with a wireless mouse used as a clicker and the Samsung Gear VR with its integrated touchpad for navigation. 41 undergraduate students participated in this research. 25 were males. They were all engineering students except for a single computer science student, with a mean age of 23 years. Also, the experiment was entirely done before the COVID-19 pandemic. Our experiment measured 2 things: the time to complete a task and the user's self-reported experience. While the former is very straightforward, the latter demands an additional explanation. We used an adapted version of the Suitability Evaluation Questionnaire for measuring the overall interaction quality. This questionnaire was originally proposed by Gil Gomes in 2013 to evaluate the usability, acceptance, and safety of VR rehabilitation software. Since the original version covers a broad range of quality factors for VR, we decided to adopt it. Our complete translation and adaptation process included dropping questions, translating and back-translating the questionnaire, evaluating the translation with expert HCI researchers, and performing a psychometric analysis on the new translated version. At the end of the day, experiment sessions were carried out like this. We welcome the participant, and we show them the devices and the research protocol. We applied a screening form to keep sensitive users from going through the test, and we ask for the participants' consent and ask them to fill out additional forms. The experiments were developed according to the recommendations of the Ethics Committee on Research of the Unipampa, and they took place in standard classrooms. The user then tried to complete one task in each device, while the experimenter counted the time. The participant filled out the adapted questionnaire at the end of the use of each device. Letting square models were applied to avoid a bias, so the order of the tasks and devices was continuously changed. Finally, we thanked the participant for helping. So, after collecting all the data, we analyzed the results in light of the research questions. Here are the mean scores of the adapted questionnaire for each device. As we can see, the mean score for Google Cardboard seems to be remarkably lower than the others. In fact, Wilcoxon's signed rank tests have revealed that participants' experiences with the cardboard are significantly worse than the experiences with other devices. Furthermore, the effect size analysis has shown that these differences are at least moderate. Participants' main comments in the only open question confirm the cardboard issues, the blurred images and the low resolution. They can be caused by the web browser rendering, we used Google Chrome for Android, or the low-quality lenses, or even both. Here are the mean times to complete tasks, this time focusing on navigation technique in each device: mouse, side touchpad, touchscreen, and mouse as a clicker. Again, the time to fulfill tasks using cardboard seems to be remarkably higher, namely worse, than the others. Thus, we applied Wilcoxon's signed rank tests again to compare samples. However, we have found no significant difference this time. In other words, we are unable to claim that users are significantly faster or slower in any device for virtual tours. So the answer to the first question is yes, the Google Cardboard delivered a significantly worse self-reported user experience than the other devices. For the second question, we were unable to detect any difference even when analyzing tasks separately. Since our time is short, take a look at our paper if you are interested in more details about the adapted questionnaire, the limitations of the study, and future work. Thanks everyone for watching our video.
Okay, thank you very much, Jean. If you want to make some questions, we are open for this. I have my question. And then cardboard seems to be the worst solution for this kind of application. What do you think about it? But for another side, it's so interesting to access to virtual reality using this kind of device. What do you think we need to have a better version of cardboard?
Well, since we really don't understand the source of the problems, we are not sure about the quality of the lenses or even the quality of the mobile phone we have used during our experiments, or even the rendering engine in the browser that we used. It's not sure saying that one of them is the only cause for the quality problems in a self-reported uh, perspective. So our guess, or our better guess, is that mainly the quality of the lenses in the low budget Google Cardboard is one of the causes. It could be bring a worse experience even if we have used another worse mobile phone.
The one we have used is a medium high quality mobile phone for that age we done the experiment. So our bet is that the lenses may be the weaker link that lead us to a worse quality.
Okay. And how long the experimental session took?
About 45 minutes, and we changed the devices, and the user needed to answer each questionnaire, the same questionnaire, in fact, after each use. So the same user, the same participant have used or have responded 4 questionnaires.
But how long immersed?
It depends on the task that the user have done, but in the average time was about 8 minutes.
Okay.
Some took less, some of them took longer.
Mm-hmm. Okay, thank you very much, Jean, and congratulations again. It was a very nice work for undergraduate students.
Thank you.
Congratulations. Okay, let's go to the next paper. Next paper is Understanding VR Software Testing Needs from Stakeholders' Point of View, and it will be presented by Estevão Andrade. Estevão, it's with you. Have a good presentation.
Hi, my name is Estevão, and I'm going to talk about the results of the paper Understanding VR Software Testing Needs from the Stakeholders' Point of View. This work was developed jointly in partnership between University of São Paulo and Ontario Tech University. By looking at the VR market, we see that there is a range of roles with different functions involved in the process of design and developing VR applications. Among them, the role of developers, designers, and users, as well as people involved in the teaching and training process of this type of technology. We note that these different roles have different functions in the process, and therefore different expectations regarding the use of this type of applications. In the context of software testing, we can observe that there is a wide range of generic practices that not always can be ported to the context of VR applications, mostly due to the low compatibility of the tools and even the absence of training material. In the view of this scenario, we then decided to understand the perception of stakeholders in relation to the use and development of software testing practices in the context of VR applications. Moreover, we defined the problem statement of this work as what are the stakeholders' point of view and needs regarding the use of software testing practices and VR applications. To do so, we decided to run a survey and investigated primarily aspects related to usability, hardware characteristics, and types of faults that can impact the experience of using, designing, and developing VR applications. To conduct the survey, we used a methodology divided into 7 stages designed specifically for construction of surveys in the context of software engineering. The steps range from the stage of definition of the objectives of the survey up to the analysis and the conclusion of the results. The survey was initially conducted during the 2019 edition of SVR and was later extended to other channels using Amazon Mechanical Turk service by inviting people who had recently purchased some VR-related projects, such as development books and VR device. The survey was also spread into specific VR development forums like Reddit. As a result, we are able to reach a final audience of 88 respondents. We are able to identify 5 different roles among the survey respondents, namely users, students, teachers, designers, and developers, who mostly use VR applications with focus on games, media, simulation, productivity, modeling, and therapy, which presents a profile of VR application usage mainly between daily, weekly, and monthly activities. In the second phase of the survey, our objective was basically to understand the perception of stakeholders regarding their perception about software testing practices in the context of VR applications. To do so, we observed stakeholders' opinion regarding aspects that could cause some impediment in VR experience, specifically if malfunctions or bugs contribute to a negative experience using VR applications. The results in the figure on the left demonstrate that most respondents agree with the statement, noting that software testing is indeed a critical activity that must be addressed in the context of VR application development. In addition, we investigated the perception of stakeholders regarding problems in specific aspects of characteristics in VR applications. The figure on the right shows a heat map which measures the criticality on a scale of 1 for minimum and 5 for maximum in different aspects existing in VR applications. Although the results point to a high degree of severity for all the aspects investigated, aspects related to visual characteristics, design, physics, and non-functional requirements such as stability and performance stand out. The third phase of the survey focused on observing hardware aspects that compose the experience of a VR application. Specifically, we look at how an application uses technical capabilities and if some disorder on those capabilities could lead to cyber sickness, in addition to characteristics linked to interaction with real-world objects and auxiliary peripherals. The results indicate a general relevance for all the evaluated aspects, with a special emphasis on features linked to A1 category that are responsible for complementing a VR perception that are responsible for functions such as object orientation, head tracking, and rotational tracking, position, and so on. Finally, in the last phase of the survey, we presented a description of several types of common faults categorized into 8 different classes and asked the stakeholders to indicate which one they judged to be most critical and important. Despite we understand that not all stakeholders would be able to recognize and identify all the faults addressed, the results of the research question 3 allow us to better understand how stakeholders assess specific characteristics of faults in relation to their criticality, in addition to discuss how each of the most pointed ons are treated in the context of VR applications. Please refer to the paper for more information about it. The main faults pointed out are related to artificial intelligence, visual aspects, and those linked to non-functional requirements, aligned with the perception presented in the second phase of the survey. The results of this work enable us to draw some conclusions from different points of view. Looking from the perspective of a quality assurance team, the results allows us to understand how to balance the activities to reach both the demand from the project development and the expectation of the players involved in the use of VR applications. From the point of view of a researcher, it allows us to develop new techniques and test approaches that handle aspects considered important by the players involved in the universe of VR application, reducing the bias from the point of view of the researcher. As feature works, we intend to extend the evaluation of the survey, collecting a great number of opinions from stakeholders so that we can have a more precise view of the needs of each role individually. In addition, to investigate the results of the study from the point of view of software testing researchers, in order to propose new testing approaches to the VR domain. Thank you.
Thank you very much for your presentation. And let's see if you have questions for you in WOVA. I'm not sure people are using it a lot. Okay. Firstly, thank you very much for conducting this kind of survey. We know that it takes a lot of time to do, but it's very useful for the community, for the developers community.
Yeah.
And one of my questions is, In fact, the problems you can find depends on the quality of the technology you are using, isn't it?
Yeah.
And for example, um, when you talk about motion sickness, it's we have each time as the time goes on, the problem is dropping. And I don't know. Do you think about to separate the results by time, for example, because the opinions of the surveyed persons depends on
On the
the
timestamp that it was responding.
yes, exactly.
Yeah. Yeah.
I don't know if you are thinking about this in separate and see the evolution of VR in time or something like that.
It's an interesting question. When I designed the survey, I didn't think about. Okay, let's make the question now, and in a future, let's see if this problem still remains. Uh, the survey was conducted last year, and in the beginning of this year. I guess that for cyber sickness, despite that we have some solutions and some investigations about it, it's still a problem. It's still a problem that remains. I got a lot of this problem. I suffer a lot of this problem, and it can be interesting for future respondents considered. Let's see if it's a problem that still remains.
Okay. Okay. Thank you very much, Stephen. And
Thank
let's
you.
go to the next presentation. Time is very short. And the next paper is the virtual reality on products usability testing, a systematic literature review. And the presenter is Fabio Freitas. Let's see the video.
Hi, my name is Fabio Freitas. I'm undergraduate student of the Professional Master Program Management and Industrial Technology at Campus Integrated and Manufacturing and Technology Senai Cimatec, located at Salvador, Brazil. Virtual reality on product usability testing, a systematic literature review. This study was performed together with PhD Ingrid Winkler, the advisor, PhD Marcos Gomes, the co-advisor, and Henrique Oliveira, the co-author. In the automotive development process, the virtual reality plays an important role on the static creation of the interior and the exterior parts of a vehicle. The motivation of this work started from the desire for clarification about how virtual reality is being used to help the automotive development process beyond the design sector. For example, modern touchable screens have been increased their presence, replaced the conventional hard buttons by touchable commands, face recognition, and command by gestures. If that in mind, could VR technology support virtual tests to anticipate issues and improve the user experience? The current physical prototypes used by automotive industry in most cases are expensive and takes too much time to be manufactured. Due to this, the prototype in VR have been adopted as a tool to support usability tests and potentially replace some physical prototype. But is there a correlation that could consider the VR a complete solution that would eliminate the need of physical prototypes? As part of our journey to investigate this subject, based on a systematic literature review and investigate about scientific knowledge available was performed, search for a study related to the application of the usability testing using virtual reality technology for products developed in the automotive sector. The methodology initiates with the scope definition, using the Peacock framework to define and organize the essential concept of the research. With the Peacock framework created, the scope with two main quests were formulated. To search for published studies on knowledge bases, several string combinations were tested, but this is the string select. It's divided by usability tests, technology, virtual reality, and field of interest, automotive industries. The selected string was the first input in the knowledge bases, and it brought more than 800 documents. In the next step, some selection filters were applied that reduce the quantity of the studies. Selection filters as time periods, type of publication, scientific error, and keywords on abstract titles reduce the quantity for almost 240 studies. From this point, through exploratory reading of the titles, introductions, and conclusions, 6 studies were finally selected. It's important to mention that the majority of the documents excluded are studied out of the scope, which is product development. They are studied related to the use of virtual reality for simulation in vehicle assembly lines, maintenance of industrial machines, and virtual professional trainings. For that reason, they were excluded. A second round of verification were performed to confirm that no relevant studies were discarded. And to do that, almost 400 abstracts of the studies excluded on filters 2 and 3 were revised, but no additional relevant documents were found. Therefore, the 6 studies previously selected were the studies analyzed in details. The selected studies are recent, within a time period of 4 years. About the system that were evaluated, the multimedia system appears as the system most used. About the metrics, it's important to notice some measurement systems which were used by different studies. Here, some same usability metrics were used for different researchers. Time to complete the task, number of mistakes during the task, and system usability scale, SUS. It's used to measure the subject participant satisfaction. The results. To answer the first research question, considering the evaluated system and testing methodology applied on the studies, the assessment made on the documents follows the research statement. The result of the study present a satisfactory correlation between the testing applied on virtual environment versus those applied on physical environment. For the second research question, those are some benefits of VR in usability tests. Cost saving in comparison with physical prototypes, agility to create virtual prototype, flexibility to create and modify the virtual prototypes. For some dynamic driving tests, the use of virtual reality will not compromise the participant's safety. About the limitations of VR in usability tests, those are the main points declared. Face reading, which is the capability of the moderator to analyze the participant's face and understand their feelings. Face reading is difficult when the participant is using the head-mounted display. External device. In some cases, immersive experience of the participants is limited, and it could compromise the result of the studies. So, the use of a haptic device and other physical instruments like a steering wheel, gear shifter, and others are necessary to improve the immersive experience. Participant discomfort. Some participants experience uncomfortable feelings such as nausea or headaches. It also could compromise the result of the study. Based on the study found through the systematic literature review, the automotive development process could take advantage of using the virtual reality technology on usability tests, but it's not recommended the replacement of physical tests for some complex system interactions, or when the participant is not completely immersive in the environment. For the future research, a standardization method adopted by different researchers could strengthen the conclusion with robust results and discussion about the use of virtual reality on usability tests during the automotive development process. Now, I conclude my presentation, congratulate the event and all professionals involved, and I would like to express my sincere thanks to my advisors Ingrid Winkler and Marcus Gomes. Your dedication and support were essential. Thanks.
Okay, thank you very much, Fabio, for your presentation. And thank you very much for doing a survey. I know it's so hard work to produce a good survey, and I always thanks the ones that are working on this. And nice work. Your main focus was in the field of cars, automotive industry, since my understanding.
That's right. That's right. The main focus is that because I've been working for automotive company since 2003, and I see how important it is to guarantee a good usability system for our customers. So as you can see, the modern vehicles will present a different kind of interactions with the system. So large touch screens will be implemented in the vehicles. So I think it's extremely important to anticipate problems and any kind of issues related to the safety of our customer, so that usability testing in the early stage of the develop process is important, so that choose this subject.
Mm-hmm. And my question is, you mentioned that you can, of course, you can solve a lot of problems with VR, but not all the problems, and it's obvious. What kind of problem you cannot mitigate by using VR?
I strongly believe that this time it is the second part of my studies, right? In this is the first step is to understand the state of the art. But what I can see and I can answer now is something related to emotional feelings is not totally could not totally be addressed in usability tests right now. In the future, it could be changed with more immersive ways and equipments and process. But now I believe that the emotional feelings inside the doing the test could not be captured at this moment.
Okay, it's a good area to work in the future.
Yeah.
Okay, thank you very much. Congratulations again. And let's move to the next paper. Okay, the next presenter is Eder de Oliveira, and the title of the paper is Investigating Users' Natural Engagement with a 3D Design Approach in an Egocentric Vision Scenario. Is Eder there? Okay, let's go.
Investigating users' natural engagement with the 3D design approach in an egocentric vision scenario. User interfaces based on modalities such as touch, gestures, or voice are often referred to as natural user interfaces. Particularly, gesture interactions have become an adequate form of interaction. On touch devices, do well-established conventions for gestures in real life. In virtual and augmented reality, gestures are also a very natural way to interact with digital objects, but there is a lack of clear guidelines for how to design gesture-based interaction in AR and VR. This work presents an approach based on user-centered design for the usage of bare hands to control an immersive system using commercial low-end HMDs from an egocentric perspective, and built from a proposed case study methodology. Our design approach generated an interaction vocabulary, considering users' preferences, seeking a set of natural and comfortable hand poses, and we evaluated users' satisfaction in performance. So, the question remaining is, if NUIs are not just created by using modalities that can be naturally translated into interaction commands in the interface, how can we define what they are? This work addresses such issue by using a user-centered design approach to build a hand-pose vocabulary for 3D user interaction in an egocentric vision scenario. To simulate a first-person vision navigation system, FPV, we developed the FPVR game, a virtual reality environment. The FPVR game interaction design and evaluation process involved 3 empirical studies with potential users. In the first part of the work we specified a preliminary vocabulary containing the hand poses considered more intuitive to represent the actions of a character from an FPV, first-person view perspective. Secondly, we evaluated the hand poses existing in the preliminary vocabulary and built a new and more comfortable vocabulary, capturing the images required to create the dataset. Finally, we validated our results using a low-end HMD in a simple VR environment. With that we conclude that FPVR game is an egocentric vision environment with a hand pose interaction solution allowing the use of bare hands as a control for VR and head-mounted display scenarios. We used an user-centered design approach to build and test the hand-based 3D interaction vocabulary. Firstly, with the questionnaire application was possible to select the initial vocabulary according to the user's preferences. Secondly, with the Wizard of Oz technique was possible to validate the preliminary vocabulary and also generate a large dataset, 58,868 RGB images, which we made publicly available. Finally, with the user's tests was possible to assess how natural the hand pose interaction was and compare it with traditional interaction devices. We believe that the design approach described in this paper can be applied to design other kinds of 3D interaction such as body-based interactions, gestures interactions, and voice interactions. In a future work we intend to investigate how this approach could be adapted to support the design of multimodal interactions in 3D environments. We thank all volunteers that participated in the studies.
Okay, thank you very much, Eder, for the presentation. And let's go to the questions. I have a question. How many users you had in your user tests?
I don't speak English. Listen.
Okay, perhaps you can move to Portuguese. Eder, quantas pessoas fizeram parte do experimento?
Foram 3 experimentos diferentes, né? No primeiro experimento nós tivemos um grupo maior de pessoas que nós distribuímos um formulário. Apesar dele não ser, não estarmos em pandemia, nós tivemos que fazer ele online para pegar esse maior número de pessoas. Foram 167 pessoas, né? Teve algumas, acho que teve 30 pessoas dos Estados Unidos, o restante do Brasil, a maioria universitários.
Uhum.
E aí nós tivemos um segundo experimento. Nesse nós trabalhamos com 15 pessoas, né? Onde nós capturamos a base de dados né? E um terceiro experimento que nós trabalhamos com 20 pessoas.
Tá legal. E quanto tempo mais ou menos durava cada teste nesse último experimento?
No último experimento, era em torno de 5 minutos a cada dispositivo, né, que o participante utilizava.
E qual é o dispositivo que vocês usaram para reconhecer os gestos?
A gente utilizou um celular normal, né, na época, parecido com um cardboard, na verdade, a gente pode considerar um cardboard, a última imagem do vídeo, né, poderia usar, a gente usava um cardboard mesmo, e bem simples, né, era um celular e a câmera do celular, para fazer o reconhecimento. E o dispositivo era feito via wireless, né, passava para o computador, onde ele fazia a inferência e devolvia o label, né, para ser utilizado no jogo.
Vocês teve muito problema de erro no reconhecimento do gesto?
A início, sim, né, nos primeiros testes de bancada, antes até dos experimentos, né, os testes pilotos, nós tivemos dificuldade com a maneira com a qual a gente pedia para que as pessoas gravassem esses gestos, né? Então, como nós fizemos o primeiro formulário, dê uma olhada como que você faria o gesto tal, imagine que você está usando um óculos, né? A pessoa naquele momento nem tinha um óculos, né? Num outro momento, nós pedimos para que eles gravassem um vídeo, eu simulei, mandei um vídeo para que eles tivessem uma ideia de como fazer, mas só que ficava muito mecânico, né? Então, quando a pessoa realmente foi utilizar, né, o ângulo era diferente, né? Tinha alguns que gravavam de ângulos completamente diferentes, daí onde surgiu a ideia de a gente mudar o contexto e passar a utilizar o mágico de Oz, que aí a pessoa teria a sensação, né, para a gente poder capturar essa base de treinamento, que ela estava utilizando o jogo de verdade e os movimentos ali eram reais, né? E isso facilitou muito no reconhecimento da base de dados, né? Depois desse momento aí que nós tivemos aí com mais ou menos umas 25 pessoas que a gente conseguiu capturar as imagens em torno de 15 a 20 minutos de cada pessoa, né? E aí começou a reconhecer muito bem, até chegou a reconhecer, nós fizemos uma gravação em ambiente interno, depois fizemos testes em ambiente externo, sem imagem nenhuma, né? Toda a base de treinamento era em ambiente interno, e teve o reconhecimento muito parecido, né? Na verdade, até os resultados foram mais positivos do que anteriormente, com o pessoal dentro, né? Acho que o cara estava mais à vontade, que estava ao ar livre.
Tá legal. Muito obrigada, Ed. Okay, this was the last paper of the session. We survived to the session. Thank you very much for being here, and hope to see you all of them personally in SVR 2021. Thank you.